Hi, welcome to this sample interview. I'm Andrew, a third year physicist, and I'm joined here with Joe.
Yeah, I'm also a third year physicist. I'll be the one being interviewed in this video.
Awesome. So often you would have multiple interviews, possibly one more maths focused, one more physics focused. In this interview, we're going to try and include maths and physics questions in the same interview. So if you're ready, Joe, let's jump into the first question. So could you sketch for me the second derivative of y with respect to x? So that's d squared y by dx squared.
Yep.
Yep, very nice.
What's that?
And then equal to minus y, sorry.
Okay, right. So this is just a second order differential equation. So if I write this with all y terms on one side, and then what I can do is use a trial solution of the form of an exponential form, something like this. And then I can substitute this into the differential equation and find what lambda would have to be in this case.
Okay, so possibly before we do that method, could I just ask you to think possibly about the behavior of this second derivative? Like, what does it tell us, the second derivative?
So the second derivative of a function describes how the gradient of the function changes with respect to x. So the first derivative, dy by dx, describes the gradient itself. And the second derivative will describe how that gradient changes. So if the gradient is increasing, something like this, we'd have a positive second derivative. And for something like this, where it's decreasing, there'd be a negative second derivative.
Yeah, perfect. So if I could perhaps ask you to, there's a bit of ambiguity in this solution, as we'll go on to see. If I tell you that at x equals 0, this function has a maximum, could you start sketching from there, talking exactly as you have about the behavior and the sign of these gradients?
So if I just quickly sketch some axes. So this is my x-axis. This is my y-axis. And at x equals 0, we have a maximum, did you say?
Yeah, yes, please.
So I know that at a maximum, something like this, the second derivative would have to be negative because the gradient is becoming less steep. In which case, I know that my value for y has to be positive because the second derivative is equal to minus y. So in positive y, I'll draw some sort of a maximum. And this is x equals 0 here. And I know that when y is a positive number, the gradient is going to be having to get more and more negative. So we're going sort of down like this.
Yeah, perfect.
And then once I get to y equals 0, so the x-axis itself, d squared y by dx squared will be 0. So the graph will become straight at that point. There won't be any change in gradient.
Yeah.
Then as y becomes negative, the second derivative will become positive and the gradient will become more positive, or it will start increasing.
Yeah.
to what I assume would then be a minimum value. And at that minimum value, it will then start increasing. And what I think is this pattern would then continue as we go into positive y, we'll hit a minimum, and negative y. Positive y will go to a maximum, and negative y will go to a minimum. So maybe something like this.
Yeah, very nice. And at this stage, does this remind you of any functions you might have seen?
So this is like a sine curve. So would this be cos, as it's got a maximum at x equals 0?
Yeah,
or something like cos, maybe.
Yeah. Could you maybe plug that trial solution in to the expression we have? So try plugging in y equals cos x.
So y equals cos x, so dy by dx is minus sine x, and d squared y by dx squared is minus cos x, which is, as we said, just minus y. So, sorry, I think I've gone off the screen a little bit there. That's equal to minus y.
So we found, by your very nice approach of like picking out the behavior of the gradient, we found a trial solution and it satisfies. We would have got exactly the same thing using this more analytical method of solving differential equations. Coming back to the physics of this, does either the form of the equation or the solution we found remind you of any physics you might have seen?
So since it has this cos like behavior, maybe something that oscillates.
Yeah, perfect.
So if we let our horizontal x-axis maybe be a time, then this would describe something that oscillates in time.
Yeah,
maybe.
Very nice. Specifically with this, it's proportional to minus the displacement, so we'd call this simple harmonic motion.
Yeah.
Perfect. Nice,
Yeah.
Very well approached. If I could just ask you to move slightly to the right in this screen, we'll move on to the second question now. I'll just work out where your cursor is. Perfect. So the next question is, can you think of the material property that will decide whether something floats or doesn't float?
So for something to float, it has to have a lower density than the liquid, say water, that it's floating in. So water has a density of 1 gram per milliliter, or whatever sort of unit you use. So if it has a density less than that, it will float.
Yeah, very nice. Do you happen to know the equation or the expression for the force that causes that thing to float? Is that some physics you've seen?
I think so. So that would be the buoyancy force.
Yep.
I think maybe I've seen somewhere, is it something to do with Archimedes' principle?
Yeah.
Where the weight of the water displaced by the object gives the buoyancy force felt by that object.
Yeah, exactly that. As an exact mathematical expression, perhaps I could just get you to note this down. We would say that the buoyancy force, let's call that FB.
FB. Oh, I think I might have gone off the screen. Sorry.
Oh, yep. Yeah, I found you. FB is equal to the density of the fluid times by the gravitational constant little g, well, acceleration due to gravity, and then the volume of the material that floats that's below the surface. So that's the volume below the surface.
Yeah.
Okay, so using this expression, if I told you that a sphere floats in water so that exactly half of its volume is below the surface, can you find an expression for me that links the density of the sphere and the density of the water that it floats in?
So if this is the surface of the water,
Yeah.
Sorry, an expression for the, what was it?
So it's between the density of the fluid that this sphere is floating in and the density of the sphere.
So I'll call that rho F and rho S.
Nice.
Okay, so I know that for this sphere to stay in its position, the forces on it have to be balanced. So I've got a buoyant force pushing the sphere up, and its weight, mg, pushing the sphere down. So for this to float, I have Fb equals mg. Fb, as you said, is equal to the density of the fluid times by gravity times by the volume below the surface. So this is a sphere. So, and we've got half of it below the surface. So that would have a volume of 4/3 pi r cubed divided by 2. But I could equally say that the mass of the sphere, so m of the sphere is just the density of the sphere times by its volume.
Mm-hmm.
So I can equate that to rho F times G times V over 2. And I had, oh no, I need a G there and a G there.
Yeah, nicely spotted.
So what I should get is that the sphere has half the density of the fluid, which I think what we'd expect.
Yeah,
if it floats half of it in the water.
Yeah, that's exactly what you said qualitatively to me about it having to be related to the volume of water displaced will be the same ratio as the ratio of the densities. That's Archimedes' principle. Okay, very nice. So extending this problem, if we say that we displace this sphere, we might press it down slightly so that it's displaced by a small distance y, and then we release it, what would you expect to happen?
I'd expect, so when you displace it a little bit, there'll be more water displaced. So the buoyant force would increase, causing there to be a net upward force, which would move it back up. And then, so I imagine it would bob up and down and sort of oscillate like that.
Yeah, exactly true. And we see that a lot with objects that float in water, right?
Yeah.
If you see ships on a harbour, they often bob up and down. Okay, diving into that a bit more. If we say explicitly that it's displaced by a small distance y, and that's downwards, so it's pressed down by a small distance y and released. Could you find the period of these oscillations for me?
Okay, I'm just going to draw in another slight diagram to make this a bit clearer.
Yeah.
So I now imagine
maybe let's exaggerate it a bit so that the water is clearly coming up by a certain amount.
So at equilibrium, the sphere was in this position. Mm-hmm. So we've pushed the sphere down a distance y. So there's been an additional, there's now additional volume below the surface on top of the volume that was required for it to be in equilibrium, which was this area here, this volume here, sorry.
Yeah.
So the additional volume we have below the surface is this volume here. So if I can find an expression for that volume in terms of y, then I can find the increase in the buoyancy force.
Yeah.
Because it's a sphere, would I consider the radius of the spheres changed, or are we in the sort of limit where I can assume that the radius isn't changing very much as I push it down?
Exactly that. Let's assume that this displacement y is quite small, so that we can assume that the radius doesn't change. So what shape will we then be trying to find the volume of? What can we approximate this extra volume?
So if the radius isn't changing, we're just moving up by a distance y. So we've got a sort of circular cross section, like a thin cylinder, maybe. Which would, if we're at the center of the sphere, because it's the equilibrium point is at its in the middle, that cylinder would have a volume so pi times the radius of the sphere squared times that small displacement we've moved y. And then as you the buoyancy force is therefore equal to well, if the buoyancy force acts upwards and we've moved it we've moved it downwards with respect to the direction of the force, then I need a minus sign there. Rho of the fluid times pi r squared y.
There's one thing missing from the expression for the buoyancy force that we had before.
G. Put
Yeah,
that in there. Okay.
Nice.
So this has got the form of simple harmonic motion then, because the force is just the mass times the acceleration. So we can say that the acceleration is equal to minus rho f g pi r squared over m times y. And that's the condition that we need for simple harmonic motion.
Yeah, nice.
So for simple harmonic motion, I know that acceleration is equal to minus omega squared y, or the displacement variable.
Yep.
Where omega is 2 pi divided by the period of that motion.
Yeah.
So what I can do is read off from here what my omega squared has to be. So this bit, that constant in front of our y is our omega squared, which is rho f g pi r squared over m. So omega is 2 pi over t is the square root of like that.
Yeah, perfect. And then we could rearrange for t.
Yeah.
One thing, because we have an expression that links the density of the fluid with the density of the solid, do you think there's something you can simplify inside this expression that would be to do with the density of the fluid and the mass of the sphere?
So I know that the mass of the sphere is the density of the sphere times by its volume. And I know the density of the sphere is just the density of the fluid divided by 2 times the volume of the sphere. So I could write rho f over m, I could write this as 2 over the volume of the sphere. Yeah, which is 2 over 4 over 3 pi r cubed, which gives me 3 over 2 pi r cubed. So I could plug that into there, which then gives me 2 pi over t is the square root of 3g over 2r.
Perfect. And I'll save you the last step of rearranging, but yeah, we can multiply 3 by t and divide 3 by this factor on the right hand side. Very nice. We noticed that at one point we had to make this assumption that the displacement was small. We've made another key assumption in solving this problem. Can you think about one of the things we assumed when we had this original condition that the density of the sphere and the density of the fluid would be ratio 1 to 2? Not ratio 1 to 2, ratio.
Yeah. Would it maybe be that the sphere is the mass of the uniform density of the sphere?
Not quite. I'm thinking more about what's above the sphere. So.
Oh, so do we assume that the contribution of the, so if we assume it's just air maybe above the sphere,
yeah,
then there's like there would also be a buoyancy force on the sphere due to the air.
Yeah.
So some of the sphere's in the water, some of it's in the air. So we assume that that buoyancy force in the air is negligible compared to the buoyancy force due to the water, because the air has about a much lower density than water.
Yeah, very well reasoned out. That's exactly it. Okay, nicely tackled. If we could move to the right again, and we'll move on to the final question of this sample interview. So this question imagines that you're stood on the beach and you see someone out at sea who needs saving. So you're going to be running from a position on land towards the sea and then swimming out to someone who's in the sea. So if you could perhaps draw a diagram that has a horizontal line that represents where the beach and the sea meet, and then a point A at the top left and a point B somewhere towards the bottom right.
So maybe like that.
Yeah, perfect. Now, as you can well imagine, you're going to be running faster than you're swimming. So perhaps we could say that the speed at which we run on land is u, and the speed with which we swim is going to be v.
Okay.
Perfect. So what do you think the best path might be for you to get from A to B in the shortest amount of time?
So intuitively, what I'd think is that because, so you said that they're faster at running than swimming, so U is greater than V. So I'd imagine I'd want to, maximize the amount of time I was running compared to as I was swimming. So maybe.
So in one solution, that would say that you should run until you're above B and you swim straight down to B. So that would be a straight line to there and then down.
Yeah.
Does that seem like the optimal solution?
I'm not sure whether it would be the optimal solution, but I think it may be something similar to that. Obviously, you wouldn't run any further past B. That would just be obviously wrong. And I'd imagine you certainly wouldn't run straight in the C from A.
Yeah.
What I think I could do is I could, if I wrote some distances on here, I could find an expression and maybe try and find the minimum of that expression with respect to time.
Yeah, that seems like a good way to go.
Yeah. So if, let's say the distance from the perpendicular distance from the C to where I am, I'll call L, and for land, and S to the person out at sea from the sea.
Yep.
I'll then call the distance, the horizontal distance between the two of these. Ooh, I don't think that line is on the screen, but I'll do it here. I'll call that a distance D. And so these are my sort of fixed distances, and I'll create now a variable X. And I'll call that the position where I enter the water.
Yeah.
So I'm sort of making the assumption here that between running to the water and then swimming to the swimmer, I'm going to be going in straight lines. I think that's quite, that would make sense. So,
yeah.
What I can do is then just find the distance between these points, find that distance, and then use the speed to calculate how long that time would be.
Mm-hmm.
So from A to where I enter the water, I'll call that point P. So the distance A to P is going to be from Pythagoras' theorem, just the square root of x squared plus L squared. And the distance from P to B is just going to be the square root of this distance here, which is just D minus x squared plus S squared.
Nice.
Could I move over to the right just a little bit to get myself a bit more working space?
Yeah. Nice.
Sorry about that. So I know that speed is distance over time. So the time taken is just the distance I travel divided by the speed going to that point. So if I call the time on the land T1 and the time in the sea T2, I get that T1 is root x squared plus L squared over U, and T2 is root D minus x squared plus S squared over V. So the total time T is going to be the square root of x squared plus L squared over U plus the square root of D minus x squared plus S squared over V.
Nice. And then your initial argument was that you were going to optimize this expression.
Yeah, so what I can do is then differentiate this time with respect to x, and that would give me the minimum, the value of x that would give the minimum time taken.
Mm-hmm.
So if I do dt by dx, that gives me, so this is x squared plus d squared to the half, so I get a half times 2x times x squared plus d squared to the minus half over u, plus 1/2 times 2d minus x times d minus x squared plus x s squared to the minus half over v. So I can rewrite this as x over the square root, x over u, 1 over u times that, times x squared plus d squared, plus 1 over v times d minus x over the square root of.
There's one thing you might have got wrong about this second differential term. When you differentiate the bit inside the brackets, d minus x. You're differentiating with respect to x.
Oh yeah, that would be
so d minus x is fine. But
is that d minus x?
What happens when you differentiate minus x with respect to x?
Oh, I'd get a minus sign out in front of it as well.
Yeah, perfect.
Yeah. Okay, so that is then, yeah, put a minus there, and then that's just d minus x. I could write it like that.
Yeah, nice.
Okay, so then I get minus that, and to minimize that, I say this is equal to 0.
Yep.
So I get 1 over u times x over the square root of x squared plus d squared equals 1 over v times d minus x over the square root of d minus x squared plus x squared. So in theory, I could then solve this for x. I could square both sides to get rid of the square root signs. And then I'd end up with a quadratic in terms of x.
Before we do that, because that seems like quite a lot of work, quite horrible expressions to be rearranging. Do you recognize these algebraic expressions? Do they look like anything you might have seen?
Like these ones here?
Yeah, possibly if I could get you to draw some angles on this diagram. So perhaps if you could draw angles that go between the paths you made and either to the horizontal or to the normal.
So if I drew something like these angles here, maybe?
Yeah, that sounds good to me.
Okay, I'll call theta 1 and theta 2 maybe for these angles. So these are just going to be the angles made here and here.
Yeah.
This diagram's getting a bit cluttered, but they're getting some sense.
Yeah.
Oh, so x over the square roots, so that's this square root of x squared plus d squared, is just that length. That's going to be the sine of the theta 1 angle.
Yep.
So this is just sine of theta 1, and I assume, yeah, so for the next one I get d minus x, which is just this distance, divided by this hypotenuse here, which again is just going to be sine of theta 2.
Right. So perhaps just rewriting that final line again.
So I get sine of theta 1 over u equals sine of theta 2 over v.
Nice. That's a much cleaner expression that we've got.
Yeah. Yeah.
From that expression, or possibly this diagram you've drawn, does this remind you of any physics you might have seen before?
Now that I've drawn those angles on, looking at my expression, it's very similar to Snell's law for refraction, I think. So if this was light traveling between 2 points going through a medium with a lower refractive index into a higher refractive index, so air into water, for example, then it would follow this kind of expression where u is the speed of light in the lower refractive medium, and v is the speed in the slower medium, with a higher refractive index.
Yeah. Could you write for me a quick expression that relates the refractive index to the speeds in the various media? So perhaps an expression for the refractive index of running on land. So it's
so if let's say running on land maybe has a refractive index of 1, or yeah, which means, so by analogy to light, then we're saying that running on land is like lighting a vacuum. So n equals 1, yeah, because n is the speed of light, or the speed in a vacuum, should we say, divided by the speed in that medium. So if we just, well, whether the land is the vacuum or not, we can just have some reference speed c. So we just basically have that n is proportional to 1 over the speed in that medium. So in other words, I get n times the refractive index of the land times sine of that angle is the refractive index of this water or the sea times sine of θ2, which then looks exactly like Snell's law.
Yeah, perfect. And in actual fact, what we've done here is, by this method of optimization that you went for, we've derived Snell's law, using the assumption, as you said, that light would take the path that's the shortest amount of time, which is Fermat's principle that allowed you to derive Snell's law. Perfect. That was all very well answered. Thank you for your time, Joe.
Great. Thank you very much.